Hello and welcome to another lecture of classical motion of a single particle. So, last time we started discussing about the concept of reference frame, and we said that a reference frame is essentially consisting of three things. One is an observer, and then for the observer to conclude about the motion in a quantitative way, the observer needs to have some distance measuring instrument, okay, or which we in general say that it needs some scale or something like that, or a measuring tape, or theoretically you can simply say that the observer is actually associated with a coordinate system. Okay. Then we said that observer, in order to measure the motion related quantities, for example velocity, acceleration, the observer also needs to measure the time interval, okay, and that is why she or he needs a watch or a clock. Okay. With these three, a reference frame is constituted, and then we talked about the concept of inertial frame of reference. We said that an inertial frame of reference is the one where the Newton's laws of motion, at least the first two laws of motion what we discussed, they are intact. That means, exactly if you see a particle with respect to an inertial frame of reference, and if the particle is free from any net external force, then the particle will always be at rest or will move with a uniform speed. Okay. Now, the point was that how to really make sure that the inertial frame itself is inertial, okay, or not. Of course, the answer is it is pretty difficult for the observer to determine whether it has some force on it or not, and that is why he or she will simply match whether F is equal to ma for that observer or not. If F is equal to exactly ma, then we can say that the Newton's second law is valid in my frame of reference, then I am an inertial frame. Okay. And then also we said that it makes an equivalence between or among all possible inertial frames of reference. And then also, once you have this type of a classification, then we can also realize the fact that an inertial frame of reference in principle should be either at rest or moving with a constant relative velocity with respect to the other inertial frame of reference. Now, of course, here I assume that you have the basic concept of relative velocity. So, a relative velocity of a particle with respect to an observer is nothing but the vector difference of the velocity of these two entities. For example, if in my frame of reference I conclude that F is equal to ma, and in any other frame of reference the person is also concluding that F prime is equal to ma prime, and from our knowledge we know that these external forces are same, then of course, if both of us we are inertial frame of reference, then A should also be equal to A prime if we say that the mass of the particle is also constant. Okay. If also, and that conclusion was also not very difficult to understand, because here we somehow assume that a mass of a particle can be at least an explicit function of time. So, if we just say that I assume that the mass of a particle is not changing with time, it is constant. So, if it is constant in one inertial frame, then it would be also constant in another inertial frame of reference. Okay. Then we said that two inertial frames of reference can be related by Galilean transformation, or more precisely the space and time coordinates of two inertial frames of reference can be connected by Galilean transformation. Now, Galilean transformation simply said that if you have two frames of reference, one without this prime, that means I am just taking let us say a 2D frame of reference, okay, two dimensional coordinate system, okay, and the observers are sitting at their centers of the coordinate systems, then we can say that if this reference frame with the primes and this reference frame without the prime, they have a relative velocity u, which is for example the capital U, which is constant, and just for the simplicity we can think that this frame of reference is just moving in the positive x direction, then you can actually have. So, just for example x prime will be equal to, or anything, I mean this is, yeah, just the space coordinate in the prime coordinates will be simply equal to x minus u t, but of course there is no movement in the y direction. So, y prime will be equal to simply y. Okay. We can generalize the this version for Galilean transformation, and we said that okay, actually if you even assume a third dimension which is z, okay, we actually can do, I do not know, like so that, yeah, x y z. So, this is completely okay, yeah. Then, and we have a u which is constant, but also can have components in 3 possible directions x, y and z. Then of course, you can have x prime will be equal to x minus u x t, y prime is equal to y minus u y t, and z prime is equal to z minus u z t. Okay. Here the first condition of transformation which I did not mention now is the uniformity of time in 2 reference frames, 2 inertial frames of reference. Okay. So, that means we also assume that t prime and t will be the same. Okay. So, that means if you and your friend have 2 clocks, then and if you just start your clock simultaneously and stop simultaneously, then if you measure 5 seconds in your clock, your friend should also measure 5 seconds in her or his clock. Okay. So, this set is known as Galilean transformation, and this is in consistency with the concept of absolute space and time. Okay. Now, I am not going very much in detail of this. So, if you go through the postulates of special relativity, okay, and then you will see that this space and time coordinates, they are not absolute and not uncoupled, they have a coupling between them, and they are related by the so called Lorentz transformation. And Galilean transformation only becomes as a limit of Lorentz transformation, where the velocities of the particles which we are thinking, the velocities which we are considering, okay, for studying the mechanics, they are pretty low, sufficiently low with respect to the light speed at vacuum. Okay. So, now we also said that this was necessary to make sure that the laws of physics, that means the dynamics physics, are the same in all inertial frames of reference. And what is, for us, what is the law? The law is F is equal to m a. Okay. So, you can now actually, so that was one way to represent Galilean transformation. Now, you can actually represent the Galilean transformation in the other way around. That means, if you have, let us say, 2 frames of reference, okay, and we do not know that how they are behaving with respect to each other, okay, at least we know that there is a point P whose motion we are studying, and the radius vector or the position vector of P with respect to this unprimed frame is given by OP, okay, or small r, and this radius vector or the position vector of P with respect to this primed coordinate is given by O prime P, which is nothing but r prime small r prime vector, okay, and the position vector of the center of the primed reference frame with respect to the center of the unprimed reference frame is given by capital R. Okay. And we also know that you can draw a triangle always, and by the rule of triangle vector addition, okay, you can simply write r is small r is equal to capital R plus small r prime, because OP in this triangle, okay, OP is equal to vectorially OO prime plus O prime P, that you can see from this picture. If you have this, you can also write ddt of r vector is equal to dr dt plus dr prime dt. Now, here you see I can make ddt all over this thing, and this t is the time defined in any of the reference frames, because they are equal. We do not have to think that this is the time of which frame of reference, this is the common time. Okay. And if I now say that this one is u, that is the velocity of the primed reference frame with respect to the unprimed reference frame, then of course, we can say that dr vector dt is nothing but u plus dr prime dt, and then you can simply say that okay, my dr prime dt is equal to now dr dt minus u. Okay. And now, if you assume that this u is constant, then only you can say okay, if this one is an inertial frame of reference, if u is a constant, that means this is another frame of reference which is moving with respect to an inertial frame of reference with a uniform relative velocity. That means that the second one is also an inertial frame of reference, and I can actually then connect. So, this is a constant, then I can connect the positions like this, and I can say that here we assume at t is equal to 0, r 0 at t is equal to 0, okay, r prime is equal to, or r prime 0 will be equal to r 0. That means, the two centers or the two origins of the two coordinate systems or two frames of reference coincided at t is equal to 0. Under that approximation you have this, and this is nothing but Galilean transformation. Okay. So, Galilean transformation is not something mysterious, it is the simple vectorial transformation between the space coordinates when two frames of reference are moving with respect to each other with a constant speed u. Now, if u is not constant, here at this point of course, we have to take into account of that. Okay. So, what happens that I can simply say that u is, if u is not constant, then I can go actually one step further. Okay. If u is constant, of course, then you actually know that you have d2r prime dt2 is equal to d2r dt2. That is our claim that the laws of physics are the same, okay, and that is exactly holding good over here. If u is not constant, okay, if u is not constant, then of course, even if one can be an inertial frame of reference in which Newton's law is holding good, the other one is accelerating with respect to this, and we can simply say, let us say then d2 r prime dt2 will simply be equal to d2 r prime, sorry, not non, yeah, r without prime dt2 minus du dt. Okay. And so, this is the acceleration of this primed frame of reference with respect to this unprimed frame of reference, and that is why if you now write m d2 r prime dt2 is equal to also m. So, m prime they are same, that is our assumption. is equal to this minus m du dt. Okay. Now, this part basically relates two frames of reference even when there is a relative acceleration. Okay. But let us say one of the frame of reference is the inertial one, and I assume for my convenience that this unprimed one is the inertial one, and that means this will be equal to F external. Okay. Then what will be the expression for the Newton's second law for the primed frame? For primed frame you will have actually m d2 r prime dt2 is equal to F external minus F of the frame. Okay. So, this is just the acceleration of the frame times the mass of the particle which we are thinking. So, this is the, I can write, I just call this F of the frame. So, this is a term which comes as an extra, and this comes to show the disparity between this thing and this thing. So, if this one is 0, then you will simply have your Newton's second law to be valid in the primed frame as well, because F external is equal. So, if F frame is non-zero, if F frame is non-zero, then m d2r prime dt2 will not be equal to F external. Okay. And you need minus F frame to be added to F external for Newton's second law to be valid in x prime, y prime, z prime frame. This extra term is known as pseudo force. So, this pseudo force is not a physical force. So, although we know that if you are in an inertial frame of reference, there are two things which are happening. One is the acceleration of the particle p, and then there is an external force F x. Okay. Now, F frame is just coming in order to balance between the m d2 r prime dt2 and F x, which are no longer equal in a non-inertial frame of reference. Okay. Of course, here you will see that this pseudo force, although they do not have any existence, they are just like a ghost force, they are of super importance in nature, because these pseudo forces are experienced by the observers which are in a non-inertial frame of reference. Now, you can ask me the question that why we are concerned of such forces. If you remember that we all are living on earth, and the earth is moving, it is actually rotating with respect to sun, and it is also spinning with respect to its own rotational axis, okay, or axis of spin. Okay. So, if we are just thinking of any single human being who is observing or measuring some phenomena in space, then that person who is measuring is actually sitting on earth, who is actually spinning and rotating and thereby getting accelerated, because you know any rotational motion is always giving you some acceleration. Okay. And when this is accelerating, then you can no longer use F is equal to ma, and you have to have some knowledge about the pseudo forces. I am just giving you two simple examples of some pseudo forces. For example, let us say I am just putting somehow a particle in space where there is no attraction of earth. So, there is no gravitational attraction due to earth. Okay. The particle will stay at some point, okay. It will float, okay, in space, okay, because there is nothing called weight. Now, the particle is just at rest, it is not moving. Now, I personally try to measure the particle, but I sit in an imaginary lift, and the lift is actually moving upward with an acceleration which is exactly equal to g, which is somehow equal or very close to the value of Earth's gravitational acceleration. Okay. So, what I will see when I am moving upward, the particle is raised. All of you can use your intuition and common sense, and you can understand that we will see the particle is actually falling. That is the relative motion, you all understand, right. But now that particle is not falling uniformly, it is actually falling with an acceleration with respect to me, it is the particle is falling with an acceleration which is g, and it is falling downwards. Although we know, although someone who is sitting very far and sitting statically or sitting stationarily in space can see that this particle is actually not moving. Since I, who is measuring the particle or who is studying the motion of the particle, is going upward, for me the particle is moving downward. I am moving with some g upward, the particle is moving apparently with respect to me with a g downward. So, for me what would happen? I will not distinguish that whether the particle is really at space or the particle is actually in the field of earth. For that, of course, I have to have or I have to gather some knowledge about my own acceleration. If someone tells me that, well, you are actually moving upward, then I will be very aware, I will say, oh, okay, then I have to actually, in order to understand the proper motion of the particle with respect to as seen by an inertial observer, non-accelerated observer in space, I have to actually give a negative acceleration to that particle, so that my conclusion and her or his conclusion remain the same. So, then I will say, okay, now I know that I am moving upward with a acceleration g. So, I now give the particle an acceleration, okay, and the particle is actually moving an acceleration, what I am seeing is downward g. So, I am giving it a negative acceleration in the downward direction, that means it will be a positive acceleration in the upward direction, which finally when I calculate the net acceleration of the particle, then I will actually find that particle is actually not moving, and then I ask the person who is sitting far in the space that is it true that the particle is actually not moving, then the person will say yes, that is true. So, now the extra part which I am just adding to the motion of that particle, the extra force which is minus mg, I mean I am just assuming that g is positive downwards in this case. If I add the term minus mg, that minus mg will be a pseudo force for that, I mean a pseudo force which I had to add due to my non-inertial situation. Okay. So, same thing whenever let us say I am just trying to study the motion of a planet, motion of a star, motion of a spacecraft, motion of a I do not know some comet, motion of an asteroid from earth, we always have to think and we always have to get convinced that we are on a non-inertial frame of reference, and according to that we have to calculate the appropriate pseudo forces, and by adding them or by superposing them to the motion of the observed particle, we can finally will conclude about the motion of the particle, which will be consistent with that of the of an inertial frame of reference. Okay. Another example before I wrap up this lecture, another example is very simple. Let us say a train is moving, okay, and the train is now accelerating, let us say in some horizontal direction plus x. Okay. I can also draw this. So, a train is moving in this x direction, okay, and then I am just saying that it is accelerating with an acceleration a. Okay. Then what will be the acceleration of any person who is sitting at rest inside the train? Of course, with respect to a person who is standing on the station, this person will also have an acceleration e. But with respect to train, that means let us say train has decided its driver to be its representative observer. Okay. So, now what will be the acceleration of this person with respect to the driver? The driver is moving or accelerating with a, and this person is also accelerating in the same direction with the same acceleration. So, the relative acceleration of this person with respect to the driver will also be 0. Okay. Now, can you tell me one interesting example? Let us say in the train I now have, from the vertical ceiling of the train, I now have a simple pendulum which is moving, okay, and you know that the simple pendulum is also acted upon by its own weight and also the tension of the string. Okay. Now, my question is, what will be if now the train is accelerating with an acceleration a with respect to the station. So, what will be the motion of this pendulum with respect to an observer standing on the station and also with respect to an observer who is sitting inside the train? Okay. You think and you let me know. Finally, just to conclude, if I have this type of equation that m d2 r prime dt2 is equal to m d2 r dt2 minus m du dt, I can say that this is the acceleration. I can, for the time being, I can actually think of a uniform acceleration. If the acceleration is uniform, then the corresponding, just like Galilean transformation, a much more general transformation would come into play here, and one can show that the corresponding space coordinates will now be related by simply x prime is equal to x minus half a x t square, y prime will be equal to y minus half a y t square, and z prime will be equal to z minus half a z t square. How to, and of course, finally t prime is equal to t. Okay. So, how to get convinced with that? You just do d dt, you will see that dx prime dt will be equal to dx dt minus a x t, and then you will also have that d2 x prime dt2. So, it will just, I am doing for x direction, and for y and z you can do. So, dx prime dt will be equal to dx dt minus axt, and d2 x prime dt2 you will have d2 x dt2 minus ax. You just multiply m both sides and you will have this equation. Okay. So, that is how in general we connect two frames of reference which are having uniform acceleration between them. Okay. Now, it is also to think that if the acceleration is not uniform, then can you also connect the two frames of reference, that means the space and time coordinates of the two frames of reference. Of course, it depends then on the exact nature of the acceleration. Okay. In the next lecture, I will try to connect two frames of reference of which one is actually static in space, okay, and can be assumed to be an inertial frame of reference, and the other one who is rotating with respect to the first one, and that is why it is a non-inertial frame of reference. Okay. Thank you.